Hello everyone, this is Aditya, and in this video series, we are going to talk about magic squares. As you know, magic squares is a very important topic in recreational mathematics, and the challenge of these magic squares is that we have to fill numbers in a square grid in such a way that the sum of numbers, the rows, columns, and the diagonals have to equal some number, and this number is called the magic constant of the square. So in this video series, what we are going to focus on is that we are actually going to prove that an age-old algorithm for constructing magic squares of odd order works. This age-old algorithm, which helps us in constructing magic squares of odd order, is called the Siamese algorithm. And order is basically the number of rows or columns in a square. And in this is an introductory video to actual proof of the magic of the Siamese method of construction. And in this video, we are going to see some basic terms and facts which we shall use in later videos in the proof. So let's start. So the first definition is of the Siamese method. What is the Siam method? Siam method is basically an algorithm that is used to construct magic squares of odd order. And what is order? Order is the number of rows or columns in the square. Now let's come to the next term, magic square. What is a magic square? Magic square is an n by n matrix that is filled with n square distinct positive integers. That is 1, 2, 3, so on till n square. That is, for example, a 3 by 3 matrix can be filled with 1, 2, 3, so on till 9. And these numbers should be filled in such a way that the sum of the n integers in each row, each column, and each of the main diagonals is the same. Below, I have shown an example of a magic square. You can see that this is a magic square of order 3. And why I call this a magic square? It's because the sum of the elements in each row, the first row, as you can see, it is 4 plus 9 plus 2, that is 15. The second row, the sum is 3 plus 5 plus 7, 15. The third row also, 8 plus 1 plus 6, that is 15. And similarly, also for the columns and the diagonal, main diagonal and the back diagonal, the sum turns out to be 15. You can see very easily. Next, let us come to Latin square. What is a Latin square? A Latin square is an n by n matrix which consists of n distinct symbols such that each symbol appears exactly once in each row and column of the square. So one familiar example of Latin squares you would have seen when you have solved a Sudoku puzzle in the past. What a Sudoku puzzle involves is that we have to fill the numbers 1 to 9 in the grid in such a way that each of those symbols appears exactly once in each of the rows and columns. So a Sudoku solution of a Sudoku puzzle is an example of a Latin square. So here also I have depicted an example of Latin square, which is a 5 by 5 matrix over here. So as you can see, each of the rows has distinct numbers from 0, 1, 2, 3, and 4. None of the numbers are repeating in rows and columns. So clearly this is a Latin square. And now, after learning about Latin squares, let us come to the definition of orthogonal Latin squares. So when are two Latin squares said to be orthogonal? When superimposed, each of the n square ordered pairs has to occur exactly once. So let me explain what we mean by superimposing. So here we have a Latin square L1 and we have a Latin square L2. So you can check for yourself that L1 and L2 are Latin square because they satisfy the conditions of a Latin square. So superimposing L1 and L2 means taking the corresponding element of L1, taking an ordered pair of the corresponding element of L1 and L2. So when superimposing L1 and L2, we have ordered pairs 3, 1, 4, 3, 0, 0, 1, 2, 2, 4, and so on as the elements. As you can see, this ordered pair is formed by the corresponding positions in matrix L1 and also L2. So this position L1 and this position L2 forms are 3, 1. And similarly, you can see that 4, 3 is formed by this 4 and this 3 over here. So this set of these ordered pairs satisfy the condition that all these ordered pairs have to be distinct. So as we can see, with 5 symbols, we can form 25 possible ordered pairs. Because if we mathematically, when we take 0, 1, 2, 3, 4, cross product with 0, 1, 2, 3, 4, we get 25 possible ordered pairs by taking elements from these two sets. So when we superimpose L1 and L2, we need to get all those 25 ordered pairs and all of them are distinct. And now, since we have seen orthogonal Latin squares, let us see what is the basic idea behind the proof, which we are going to see over this video series. So the idea is that we shall be decomposing the Siamese magic square into 2 orthogonal Latin squares. And this decomposition will lead us to the proof of the Siam construction. And next definition, we shall come to traversal. What is a traversal? Traversal is a set of n cells in a Latin square of order n, that is number of rows or columns, each containing a different element and no two sharing a row or column. So this will be clear with an example, which we will see shortly. So we take n cells in a Latin square such that each of those cells should contain a different element and each cell should belong to a different row and different column. No two cells should have a same row or column. And disjoint traversals are traversals that do not overlap. And this is a fact. Set of n disjoint traversals on a Latin square of order n can be relabeled to form a new Latin square. So this is an important fact because we shall be using this fact in later videos to prove that a magic square can be decomposed into 2 Latin squares. So this is the fact we shall be using. And this fact also I shall prove in another video if possible. So this is the example of traversals. So as you can see in this, find all the elements marked with a triangle over here. So 0, 4, 3, 2, 1 are marked with a triangle. And you can see that all the cells which are marked with triangle have distinct elements in them. They do not have the same number in them. And also, they belong to different rows and different columns. And you can see 5 different traversals of this matrix L1, 5 different traversals of Latin square L1, which all are marked with different symbols. So that's it for this video, guys. Thank you, and we shall explore more in the next video.